All that we cover for the rest of the semester will be related to the concept of subgroups of groups. You've seen one. You have seen this subgroup, and in fact, for homework, you're going to prove that this is if G is a group and A is an element of G, that the cyclic subset generated by A, in other words, all integral powers of that element, forms a subgroup. You're showing that it is a group. We're going to call it a subgroup of G. So that's your first example, and now let's go on to define exactly what a subgroup is. Now you want to put this on pause right now and make sure that you get this into your notes. It's in handout 3. If G is a group and H is a non-empty, that's part of the definition, a non-empty subset of G, then if H with the same operation as G, H delta, is also a group, then we call H together with delta a subgroup of G. And we write H is a subgroup of G. So it's a non-empty subset of G, which is a group all by itself using the same operation as G. That's what a subgroup is. Now remember, it's more than just a subset. H is a non-empty subset of G. Both G and H are groups, and both G and H must use the same group operation. So you're always considering it as a subset of the group, and it is a group itself under the same operation as G. And to make sure that we understand the definition, let's look at these 3 examples. GL2, R, I left out the real numbers there. The general linear group under addition, it is a subset of all 2 by 2 matrices with real entries. But is it a subgroup? Well, no, for many reasons. But the one we could think of easily is that it is not a subgroup of this because the identity is this matrix here in the group of 2 by 2 matrices under addition, and that identity is not in GL2, R, because it has a 0 determinant. So GL2 is not a group. Therefore, even though it is certainly a subset, it is not a subgroup. The next one, we're looking at the general linear group again. Is it a subgroup of the 2 by 2 matrices under addition? Well, no. You see, the operations are not the same. So again, even though it's a subset, it's not a subgroup. And is SL2, the 2 by 2 matrices with determinant equal to 1, is that a subgroup of GL2? Well, yes, it is. In fact, just recently you proved that this special linear group of 2 by 2 matrices with determinant 1 is indeed a group under multiplication, matrix multiplication, the same operation as in GL2. And so we say SL2R is a subgroup, you use the less than sign, of GL2R. We don't usually use this notation here if the operation is understood clearly. Here's another example of a subgroup of the dihedral group D4, the symmetries of a square. K is the set generated by R squared and H. We've written it that way before. Let's write that down. Just K is, sometimes we write, instead of just putting A in here, we have 2 group elements, r squared and h. So instead of taking all powers of an element, we take all powers of r squared, all powers of h squared, and all products of those powers. And it just gives us this set. We get each of these squared is the identity, so we get right to the identity. The product of these is hr squared. And if you draw a table like this, often that's a good way to see it, draw a group table, and you'll see that all of the entries in here are simply one of those, E, R squared, H, or HR squared. So you see closure right away by looking at the table. And we know that this is a subgroup. The identity is there. The operation is function composition, the same as in D4. It's associative. We said we had the identity, and each element is its own inverse. So yes, it's a subgroup of D4. But is it a subgroup of D6? Let me change color here to talk about D6. Is this a subgroup of D6? The rotation now, R, is in D6. It has order 6. R has order 6, so it's a 60-degree rotation instead of 90. And let's write out the elements of D6. D6 has the identity r, r squared, r cubed, r to the 4th, r to the 5th, 60-degree rotations, 120 degrees, etc. And then it has h representing a flip across a diagonal, and it has hr, hr squared, hr cubed. These are all flips on the other diagonals. R, HR to the 4th, HR to the 5th. Okay, so we have 12 elements in D6, and now let's see, is this a subgroup? Well, we don't have closure, do we? Because if we look at all the elements here, we have r squared, we have HR squared, but HR squared is equal to r to the 4th h. And so we have to use this computation rule to see if we have everything. Let's see, we have h squared is e, r. Oh, r squared is r to the 4th, which is not the identity in D6. So this is not a subgroup. And I guess this would be right here. The best way to prove it is we do not have closure. We do not have closure. In other words, the operation function composition is not a binary operation on that set, because you can multiply two elements of the set, in this case r squared times r squared, and jump out. You get r to the 4th, and it's not in there. So this is not, you have to be careful before you think something is a subgroup. In this case, that set is a subset, but not a subgroup. Now you have done this proof yourself, but I'd just like to go through the steps of what you have to do if all you have is the definition of a subgroup to work with. We first have to, we have to show we have closure, check off associativity because that's inherited from the general linear group. It's a subset of that. And then we need to show the identity is in SL2. And note it's the identity of GL that has to be in there. And we have to show that the inverse is in there. So let's go through this because there's a couple things we could say about a couple of these steps. Okay, let's do closure. In other words, making sure that matrix multiplication is a binary operation on this set. Okay, so, closure, we need to pick A and B in here. Let A and B, and just for ease in writing, I'm just going to put SL. Let AB be an SL. Then we know that the determinant of A is equal to the determinant of B is equal to 1. we want to show that AB is in there. So we need to take the determinant of AB, the membership rule for SL. Well, that from linear algebra is the determinant of A times the determinant of B, which is 1 times 1 is 1. This implies that AB is indeed an element of SL, so we have closure. Number 2, we'll just mention associativity is, well, let's say inherited. For subgroups, we're never going to have to show associative because we know that we are talking about a subset of a group where the operation is assumed to be associative. So associativity is inherited from the group GL. So there's nothing to show there. Number 3, we need the identity of GL to live in SL. So we know the identity in GL is 1, 0, 0, 1, that matrix. And the determinant of that matrix is 1. Therefore, we can say that the identity does live in SL. Make note here, the identity that in the subgroup is the same as the identity in the big group. And number 4, let's get inverses. Let A be any element of SL. Now I'm going to put in parentheses here. We know A inverse exists in GL, but we need to show GL is a group, so we already know there's an A inverse. We need to show that A inverse lives in SL. But we've done that before. It's very easy. The determinant of A inverse is equal to 1 over the determinant of A. And the determinant of A is 1, so the determinant of A inverse is 1. And we can say, therefore, A inverse does live in SL. And we can conclude that SL2 is a subgroup of GL2. Now you see the process that we just went through was very similar to what you've done just to show a set under a certain operation is a group. But if we already have a subset of a group, there's really much less that we have to show, and there is in fact a subgroup criteria test that you only have to show one thing. You verify H is a non-empty subset of G, but as long as it's non-empty, you can show that it is a subgroup simply by showing that, well, if the operation is delta, simply by showing that if A, B are in H, then A delta B inverse is in H. Now, B inverse, you know exists because it exists in G. So when all we need to do is just let X and Y be in H, and then show that X, Y inverse is in H. And if you can do that, you can conclude that H is a subgroup. But we have to prove this, and this is the first major proof that we've done. So be sure and understand each step and put it into your notes. The first part of the proof is very simple. Let's go this way first. Suppose H is a subgroup of G. Let's let A and B be elements of H. Since H is a group itself, we know that B inverse exists, and I can write AB inverse is in H. Okay, so if H is a subgroup of G, certainly for any two A, B, and H, AB inverse is in H. So going in that direction was simple. Now we want to prove it in the other direction. So we suppose that AB inverse is in H for all A, B in H. We are assuming that G is a non-empty subset of, H is a non-empty subset of G, and that AB inverse is in H for all AB in H. Now this is a more significant proof. We have now to show that H is a group under the operation of G. Okay, so notice I wrote above that statement, H is a subset of G and H is not empty. Suppose that for any two AB in H, AB inverse is in H. Keep in mind we can talk about B inverse because we know that G is a group and that for any AB in H, B inverse does live in G. We just need to prove now that if this is true for any A and B, that we do have the identity. Associative comes from G. We need to know that inverses exist, and we need to know that H is closed under the operation of G. Now in this proof I'm going to do closure last, and hopefully you will see why once you see the proof. Let's go ahead, and the first thing is we need to show H is a group, so let's just mention that associativity is inherited from G. So we've got that done. Now let's see if we have the identity. All we know is that H is not empty and that for any two AB in H, AB inverse is in H. Well, H is not empty, so pick or let's call it X. Let X be in H. I don't want to, since we stated what we want to prove in terms of A and B, I'm going to use X's and Y's so you don't get them confused with how I stated it. So pick X in H. Okay, then so pick X in H, then, well, for any two elements in H, then X inverse is in H. Remember, up here when it says AB inverse is in H for any AB in H, that doesn't necessarily mean that A and B have to be different. Here we're using A as X and B as X. Well, then X inverse is in H, which of course gives us the identity of G lives in H. So we have the identity. Now let's get inverses. Inverses are in H. We know they're in G. So for inverse, let X be in H. Now we know E is in H too. So then E, X inverse, is in H using the subgroup criterion, AB inverse. So this implies that X inverse does live in H. So we have inverses, identity, and associativity. So now we need to prove closure, and you'll see why I'm doing it at the end, because I need to know that inverses exist. in order to use the AB inverse. So for closure, in other words, we're showing the operation is a binary operation on H. Let's just pick two elements. Let X and Y be in H. Well, Y inverse is in H by what we did up here. We know Y inverse is in H. So X, Y inverse inverse is in H. But that means XY is in H. Therefore, we have closure. You should go back through this proof and see each place that we used the fact that if A, B are in if A and B are in H, then A, B inverse is in H. I write that here, A, B in H. This is what we're using in each step of the proof. Implies A, B inverse is in H. That's all we could use. So to get the identity, we picked an H and H because it was non-empty, and we used our A and B both as X. So we have X, X inverse is in H. It gave us the identity. For inverses, we picked X in H and we needed X inverse. But we picked X in H and we already had proven, that E is there. So I use AB inverse. I have X, I have E, so E X inverse is in H. Here we use it again, and that gives us inverses. Now for closure, again, that's the only thing I had to work with. So for closure, I pick XY in H, and I want XY to be in H. But what we had to work with told us that XY inverse is in H. So I said we already had inverses, and I know that Y is equal to Y inverse inverse. We've proven that. So I use as my A and B, I use X and I use Y inverse. So I have A, B inverse. X, Y inverse, inverse is in H, and we get what we need. So be sure you understand how we used that one simple test only, and we can prove that if that is true, that H is a subgroup of G. So we could conclude that now, by the way. Therefore, H is a subgroup of G. Now see how easy it is. We're going to prove the same thing we did before, that the special linear group is a subgroup of the general linear group under multiplication. And look how easy it is if we use the subgroup criterion test. All I need to do, is let A, B, be in SL2, be any two matrices in there, and I need to show that AB inverse is in there. Well, to live in SL, you have to have a determinant of 1. So I'm just going to take the determinant of AB inverse. Now, why can I just write B inverse? Because I know it lives in GL. So the subgroup criterion test says if A and B are in here, anytime you pick two elements in there, is AB inverse in there? Well, to find out, we just take the determinant. That's the determinant of A times the determinant of B inverse, which is 1 over the determinant of B. And that gives me 1 times 1 over 1 is 1. Therefore, AB inverse does live in the special linear group, and we can conclude, therefore, that SL2 is a subgroup of GL2. It's that simple. And what we're going to do in class next time is use the subgroup criterion test to prove that several examples. Let me do one more that we've already done and just show you how nice this test is and how easy it is to use. let's prove that the cyclic subset generated by an element of G is a subgroup. Well, the first thing we should do is define it. So let's recall what it is. It's the set of all integral powers of the element A in G. And we want to show using the subgroup criterion test. So I'm going to let X and Y be elements of the cyclic subset generated by A. Well, then X is a power of A, and Y is a power of A. Let's say A to the M, A to the K, for some M, K that are integers. All right, we want to show that X, Y inverse is in the cyclic subset. So let's write X, Y inverse. We know, and again, we can speak about Y inverse because we know that it's in G. So XY inverse is equal to A to the M times A to the K inverse. We proved in the last class that this is A to the M, A to the minus K, which is A to the M plus minus K, and that's in the integers, so we know that's M minus K. M minus K is an integer, so X, Y inverse is in is in the cyclic subset generated by A, and we can conclude that it is a subgroup. So we can say, therefore, the cyclic subset generated by A is indeed a subgroup of G by the subgroup criterion test. Let's call it SCT. So this is the kind of work we'll be doing in class. Please study the proof and know the right terminology by the time you come to class.